Well, hopefully everybody did fairly good with section 3.1. So now we want to move on to 3.2, which is the addition rule. And I've got or underneath there, and the rule of complements, not. So if you remember back in, if you took Math 110 or if you've had any kind of set theory and stuff like that, or always talked about the union, and complements were the knots of problems. So that's where these are actually coming from. So a lot of these probabilities are directly linked to things in set theory, and we'll talk a little bit about that when they appear. So in this section, what we want to do is think about, we're going to start with the or type problems. So again, let's kind of talk about drawing a card from a standard deck of cards. And let's assume we let J denote drawing a jack and Q denote drawing a queen. What's the probability of drawing a jack? So we know that there's 4 jacks on our set of cards. So remember, our jacks are these guys right there. And then the queens are these guys. So again, there's 4 of those as well. Oops, what in the world have I done? Hold on. So finally, by looking back at the cards, so we see that the probability of rolling a jack is 4 out of 52. Probability of getting a queen is 4 out of 52. And if we look at the set of cards, we can see that there's 1, 2, 3, 4, 5, 6, 7, 8. So the probability of getting a jack or a queen appears to be 8 out of 52, which means it looks like I could have just taken these two guys, added them together, and gotten the exact same thing. So it looks like if the probability of getting a jack or a queen is just the same as probability of adding a jack plus the probability of getting a queen. So let's see if that's always true. So let's look at the next example here. So what about if we wanted to find the probability of drawing a jack or a diamond in that case? So again, the probability of getting a jack we saw before was 4 out of 52. The probability of getting a diamond is going to be 13 out of 52 because there's 13 total diamonds and they're the ones that are highlighted down below. So if what we said was above was true, then we should be able to add these together and get 17 out of 52. So is that what I got a typo here too, look at that. I gotta fix that. All right, so if that's the case, let's actually add these up. So if I look, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Whoa, wait a second. So I've only got that the probability of getting a jack or a diamond is 16 out of 52. What happened? Where did I go wrong? Well, what happened was that jack of diamonds got counted in both lists. Because notice the jack of diamonds is going to be one of those 4 jacks, and the jack of diamonds is going to be one of those 13 in that thing. So we'll talk about that a little bit later. So just kind of keep that in mind that sometimes you have to be a little careful about double counting. So for right now, what we want to do is focus on events like the first one where there was no overlap, there was no double counting or anything like that. So when that occurs, these are what are called mutually exclusive events. So mutually exclusive events are just 2 outcomes that are disjoint or mutually exclusive if they cannot both happen at the same time. So again, if you think about this from a set theory perspective, like you'd have a Venn diagram where you had 2 circles that didn't overlap at all. And if that was the case, then everything was fine. You could just add up set A and set B. And that's what we had in that first situation, because if we put jacks in set A, queens in set B, they're not the same. They're totally different cards. So it's safe to just go through and actually count those guys together. But, all right, so before we actually define what this is formally, let's actually go through and do an example just to kind of get an idea of what would happen. So again, we're going to roll a fair six-sided die. So again, just, you don't have to do this, but I like to do it every once in a while just to kind of remind me. So again, my sample space is going to be 1, 2, 3, 4, 5, or 6. And so I'm asking what's the probability of getting a 4 or an odd number. So in this case, I'm looking for the probability of a 4 or an odd. So again, the probability of drawing a 4 or rolling a 4 is just going to be 1 over 6 because there's only one 4 on our list. And so the probability of getting an odd number, let me use a different color, is going to be if we draw 1, 3, or 5. So it looks like it's 3 out of 6. And so in this case, are these guys disjoint? Yeah, so because if they weren't disjoint, I'd have one that was colored both green and blue in this case, because as I was coloring them in, I would have had to color one of them twice. But in this case, 4 is an even number, it's not an odd number, so these two things can't happen at the same time. So since these are nice disjoint events, then what I can do is I can just kind of add these up separately. So the probability of getting a 4 would be 1/6. Probability of getting odd would be 3/6. So in this case, I get the probability is 4 over 6 or 2/3 or around 67% or so. So again, if you want to turn this into decimals and stuff. So again, that's one of the other reasons I like, listing the sample space, because I can actually color things in. I can see if there's overlap and stuff by just actually looking and shading and things like that. All right, so let's look at the formal rule for how we would actually add these guys together. So again, this is only true if A and B are disjoint or mutually exclusive. And so what we get is the probability of A or B is just the probability of A plus the probability of B in that case. And if you remember from set theory, and again from the 110 class, we had this formula that allowed us to say the cardinality or the number of elements in A union B was equal to the number of elements in A plus the number of elements in B. So if you notice, these two things are exactly the same, and that's actually where this formula comes from. It actually comes from set theory in this case. Now, what if we had, 10 disjoint sets or 5 disjoint sets? Well, same rule applies. So that's what this bottom thing is. This is just kind of a generic. So for any number of disjoint sets, you can just add up all the different probabilities and get your answer that way. So if you happen to have 3 disjoint sets or 4 disjoint sets, you can just add up that huge number and go from there. But all right, so let's look at another example here real quick. And so again, if you need to, and I may scroll back at the cards just so we can look, if you need to, definitely reference the cards. So what's the probability that we get an ace or a face card? So remember, aces and face cards are totally different. So our aces are down here. Our face cards are these guys. So they're not the same. So these are 2 disjoint sets. So we can actually use our rule from above. It's the probability of an ace or a face card. So I'm just going to use F for face card, or maybe FC. So in this case, what I need to do is first figure out what's the probability of getting an ace. What's the probability of getting a face card, and then just add those guys together. So as we saw, there's 4 aces out of 52 cards total, and for face cards we've got 12 face cards out of 52 total. So again, 4 plus 12 gives us 16 over 52. And then again, you can reduce this down with your calculator, into a simpler fraction or decimals, whatever you want to do. I'm just going to leave it at this for right now, just so you guys get an idea. But this can, well, I'll go ahead and do it. I got my calculator here, so I might as well simplify it down. So 16 divided by 52 would give us 4 over 13 in that case, which is about 31% or so if you plug it in as a decimal. So it's about a 31% chance of drawing an ace or a face card in this case. All right, so what's the probability of getting a number or a red jack? So again, if we go back to our little chart here, just to remind us, so numbers are all of these guys. The jacks are just going to be these. So again, they're totally disjoint. Numbers and jacks are totally different cards. So there's no overlap between them. So I'm looking for the probability of a number or a red jack. So in this case, since there's 13 hearts and 13 diamonds, that means there's 26 total red cards, and similarly there's 26 black cards. So the probability of heck, don't ignore what I was saying. I was looking at the wrong thing. So we're looking at number cards. So sorry. So we want to know what the probability of the numbers are, plus the probability of a red jack. So the number cards, so be careful because we don't have a 1. So we start with 2. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 number cards for each suit. And there's 4 suits. So 9 times 4 gives us 36 number cards. All over 52. Plus the probability of a red jack. So there's only 2 red jacks, remember. So there's the jack of hearts and the jack of diamonds. So there's only 2 red jacks. So adding these guys together, we're going to get 38 out of 52, which again, I put this in the calculator, gives me 19 out of 26, or it's approximately 73%. So we've got a 73% chance of getting either a red card or a number card or a red jack in that case. All right, so let's look at the next one. So what's the probability of selecting a red card or a black card? So the probability of a red or black. So again, you can't be a red card and a black card at the same time. So these guys are mutually exclusive. They're disjoint. So we can use our above formula to get probability of red plus the probability of black. And so this is what I was thinking before. So there's, since there's 13 red hearts and 13 diamonds, that means there's 26 red cards total. But similarly, there's 26 black cards. So when I total these together, I actually end up with a 1. So there's a 100% chance that I'm going to get a red card or a black card. And that would make sense because they fall into basically those 2 categories. So, perfect. All right. So at this point, I've got some practice problems for you. So go ahead and pause the video, take a little bit of a break if you need to, and work through practice 1, 2, and then when you're done that, come back, and then we'll talk about that situation like earlier when you end up having an overlapping, something overlaps each other. All right. So overlapping, so what happens if they aren't disjoint? What happens if we have a Venn diagram that actually has an intersection point like we've got here in purple? We've got this overlapping intersection point. Well, if you remember anything about intersection, problem is that means it's that part in the middle is in A and it's also in B at the exact same time. So the purple is what's called like A intersect B. And it's in A and it's in B. So the idea is, and this is the reason we kind of messed up that example with the Jack of Diamonds, because the Jack of Diamonds was in the diamonds, but it was also in the jacks. So we ended up counting it in both places, when in reality we should have only counted it one time. So that's what we have to really be careful of when we have sets that are not disjoint. So again, in this case, like what we would want to do is we'd want to construct this in such a way that we're trying to find the probability of a jack or the probability of a diamond. So we saw already that the probability of a jack was 4 over 52. The probability of a diamond was 13 over 52. But the idea is, if we were thinking about this from this overlapping situation, the Jack of Diamonds is in both of these numbers. So what we want to do is we want to subtract out that overlap. We want to subtract out 1 because of that Jack of Diamonds that occurs in both places. So we want to subtract out a 1 out of 52. And if we do that, now we end up with 17 over 52 minus 1 over 52, which in fact gives us the 16 over 52 that we counted earlier that should have been the correct answer in this case. So these are the tricky ones, in my opinion. So this is another reason it helps sometimes to actually write out the sample space so you can tell, does this thing actually overlap or does it not overlap? So, because it's fairly easy to see if it doesn't overlap, but if it does, how much am I subtracting out? What am I subtracting out? And things like that. So if we look, so here's our general addition rule. And so this actually is true even if the sets happen to be disjoint. So if the sets would be disjoint, oops, I'm missing a parenthesis there. If the sets were disjoint, then A intersect B would just be 0, and this part would just end up going away anyway. We'd end up with just P of A plus P of B. So this general rule actually works for either situation, whether it's disjoint or not disjoint. So what we've got is the probability of A or B is, again, the probability of A plus the probability of B minus the overlap. So in this case, where A intersects B. And again, if we were to think of this in set theory terms, this is kind of what it would look like. So the cardinality of A union B would equal the cardinality of A plus the cardinality of B minus the cardinality of A intersect B, the thing that they actually had in common. So again, if you don't know set theory, that doesn't matter anyway, but I figured I would just tie it back in for the folks that have had some set theory in the past, just in case. All right, so let's look at some more examples here that these are going to have some overlap to them. So in this case, what's the probability that you get a king or a spade? So in this case, we've got the probability of a king or a spade. So the cool thing is we can start these all the same way, and if it happens to be disjoint, we just ignore the overlap part, and if it's not disjoint, then we've already set up, that it's ready to go anyway. So I would still go ahead and do probability of K plus the probability of S minus the probability of the overlap, just to see if there is any, just so I'm set and ready to go if there is some. So in this case, is there some overlap? So again, looking at the sample space a lot of times helps. So in this case, if I go back to here are my kings. Oops. Are all there. And then I'm going to draw what are we doing? Spades in red. And so if you ever have a situation where the green and the red are overlapping, then that means that card or cards is in both sets, and it would accidentally get double counted if we treated this as disjoint. So we can see in this case that the king of spades is in the king's column, but it's also in the spade row. So that means it's actually being double counted in this case, and we don't want that to happen. So when we go back, so this one does have overlap, and so in fact the overlap is the king of spades, which means there's just one of those. There's one card. So when we do our overlap, the probability of a king is going to be 4 out of 52, plus the probability of a spade is going to be 13 out of 52, and then we want to minus this one card, this one overlapping card, so we're going to get minus 1 over 52 in this case. So now combine everything together, we get 17 over 52 minus 1 over 52 gives us, again, 16 over 52, which was what, 8? Oh, I forgot to simplify. But anyway, but you can simplify that on your own. So that would be our probability of getting a king or a spade. And again, just being mindful of that king of spades is an overlap. All right, so let's do the same thing here. What's the probability that you get a queen or a face card? So again, I don't know whether they overlap or not, but I'm just going to start off assuming they do. And if they don't, I'll just have a 0 in that overlapping spot. So minus the probability of overlap. So now let me go back to my sample space and see if we've got any overlaps. Let me get rid of these. So in this case, we want to check queens. So we're looking at these guys. And then we're also comparing these to all face cards. So again, anywhere where there's blue and red together is going to be overlapping. So in this case, this whole middle is all overlapping. So because there's blue and red in both of those. So the only ones that aren't overlapping are just the jacks and the queens in this case. So when I go back, my overlap is actually going to be 4 cards. It's going to be the Queen of Hearts, Queen of Spades, Queen of Clubs, Queen of Diamonds. So when I do my subtraction, I'm going to get minus 4 out of 52 for those. So this one's kind of a weird one because we added the queens and we're basically going to take them all out. But it does work. So in this case, the probability of a queen is 4 out of 52, plus the probability of a face card is 12 out of 52, but then minus any kind of overlap, which is all those queens. So the Queen of Hearts, Queen of Spades, Queen of Clubs, Queen of Diamonds. So in this case, when we combine these together, basically the queens are just going to cancel out, and we end up with 12 out of 52 in that case. All right. Does that make sense using the tables and stuff like that? All right, perfect. So next example, we're using something that's called a contingency table. And so if we look, across is telling us our majors. So in this case, there are 58 right-handed education majors, 13 left-handed education majors for a total of 71 education majors. And then we've got 47 right-handed math majors, 12 left-handed math majors for a total of 59 math majors. And so total, we've got 130 people that are involved in our survey. And then if we read these up and down, so in this case I've got 58 right-handed people plus another 47 right-handed people for a total of 105 right-handed people. I've got 13 left-handed plus 12 left-handed for a total of 25 left-handed people. So that's kind of how we read the different parts of the table. And so the goal is we want to use kind of that same idea. And so again, I'm going to draw pictures so I can kind of see what overlap is there, so I can see what I may have to subtract out if I have to subtract anything at all. So if one person is randomly selected from the group, what's the probability that this student is an education major or left-handed? So in this case, I'm going to use the blue highlighter to represent all the education majors. So that's just going to be highlighting straight across. But then we want to use the orange to represent all the left-handed. So again, if we were just writing this out, we could do probability of ed, or left equals the probability of ed plus the probability of left minus the probability of the overlap. And if it turned out there wasn't any overlap, again, we could just make it 0 and move on. But in our case, any place that's going to be both orange and purple is going to be something that overlaps. And so we can see in this case that 13 is getting counted in the education majors, but it's also getting counted in the left-handed column. So that means we've got 13 out of 52 that we want to get, or not 52, 130, sorry, I was thinking about the last problem. Out of 130 that we want to subtract off so that we don't double count these guys. So in this case, our number of education majors are the 71, so we're going to get 71 over 130, plus our left-handed folks, which are going to be 25 out of 130. And then our overlap is going to be this 13 out of 130. And so finally, adding these guys together, we get 17 plus 25 minus 13. Looks like 29 out of 130. And then again, if you want to put this in the calculator and stuff like that to get it the percentage, go for it. That's good. All right. So does that make sense for everybody? All right, very good. So let's do the same thing for problem B here. So problem B, compute the probability of selecting a math major or a right-handed student. So again, I like to see things, so I'm going to go up and kind of color in my contingency table so I can see it. So the probability of getting a math major is going to be, oops, did the wrong color though. So it's going to be that row with 59 people in it, and then a right-handed student would be everything in there. So again, any place where we've got blue and orange intersecting is going to be something that's going to be the overlap, or what we're going to have to subtract out. So again, assuming we don't know whether they overlap or not, we can just kind of write this out. So probability of math plus the probability of right-handed minus the probability of an overlap. And so again, we see that the math total is going to be 59 out of our 130 plus our probability of right-handed, which is going to be 105 out of 130. And then minus any overlap. So again, this part that's in the blue and the orange together is going to be our overlap. So we want to subtract out 47 out of 130. So again, throwing this into our calculator so we can see what we get. This is another good example. If you happen to forget the overlap, when you add everything together, you're going to end up with a number that's bigger than 130, and you're going to be like, what in the world just happened here? So if that happens when you're working on a sample problem and you end up getting an answer that's bigger than the bottom number, because remember, probabilities have to be between 0 and 1. So if you get something like 154 over 130, that means we've messed up somewhere. There had to have been overlap that we didn't account for. So kind of keep that in mind as an extra check for yourself. So in this case, 59 plus 105 minus 47 gives us 117 over 130. And so again, you can plug that in the calculator to figure out what our answer is. But all right, any questions or anything about the the overlapping OR problems? All right, so here's a bunch for you guys to practice. So we've got practice 3, practice 4. So again, this is a nice contingency table that you can practice just like we did above. So the last thing we want to do is we want to talk about what's called the complement. And so there was a word in set theory called complement that you may remember. So like A complement, for example, was the set that was everything shaded outside of A, and it was denoted A with an overline. So this is the exact same idea. So this is the same idea of not A. So we want to include things that aren't included in A. So for example, let's say we want to figure out what's the probability of not getting an ace. So there's a couple different ways you can actually do this. So if I wanted to say, well, if I don't want to get an ace, well, why don't I just take this list and just scratch out the aces and not consider them at all? And so then I could go through and count all the other numbers that aren't colored out. And so if I did that, I would get 48 out of 52 in that case. And that totally works. It works all the time. Now, if your sample space is really, really big, it might be a little tricky to actually count all of them. So that can be sometimes where you run into a problem. But what you can do on the other hand is, so remember, since all of our probabilities add up to 1, so the probability of finding not an ace would be just take 1 minus the probability that it is to find an ace. So in this case, I know the probability to find an ace is 4 over 52. So now I can do 52 over 52 minus 4 over 52, which gives me 48 over 52. So I got the same thing either way. So the probability of not finding an ace is the same thing as just doing 1 minus the probability of finding an ace. So again, you can either, kind of eliminate the aces from your chart, count up all the other numbers and figure out what you get, or just do 1 minus and figure out the probability that way. So they both work, and again, that comes from the fact that we've got that rule about all the probabilities add up to 1. So in general, the complement of an event, devoted over line A, which again is what we saw in set theory, just looks like the probability of A equals 1 minus the probability that the A actually occurred, the event occurred. And in set theory terms, again, not that this matters, the cardinality of A complement would equal the same thing as 1 minus the cardinality of A in that case. All right, so let's look at an example here real quick. So if you pull a random card, what's the probability it is not a heart? So in this case, we're trying to figure out probability of not heart. So again, there's two different ways you could do this. You could go up to this table. Let me erase all this stuff. And you could say, okay, well, let me strike through all the hearts here. Let me get rid of these. And I could count everything else. So that means I'd have clubs, which are 13, spades, which are 13, diamonds, which are 13. And I could basically get the probability of spades plus the probability of diamonds plus the probability of clubs would be 13 over 52 plus 13 over 52 plus 13 over 52, which would give me 39 over 52. Or I could do it using the formula above and say, well, why don't we just do 1 minus the probability that I actually get a heart. And so in this case, I saw that there are 13 hearts. So I've got 1 minus 13 over 52. So I need to get a common denominator, or you can just type it straight in your calculator, 1 minus 13 over 52, if you don't want to do that math. Oops. And so again, when I do the math, I'll end up with 39 over 52. So either way, I end up with the same answer. So the way you do complements, again, is up to you. If you like using the 1 minus formula, that's going to work perfect. If you like just eliminating those elements from the sample space and adding up whatever's left over, that's going to work every time. So it's kind of up to you. So there's a couple practice problems here for you guys. So we've got practice 5 and practice 6. And that is it for 3.2. So this is a lot of probability. It's fun stuff. It keeps you hopping. If you have any questions, I'll be around all day, so just let me know.